So until now, we've been dealing with one or sometimes two and maximum three cash flows per problem. Now we are ready to tackle annuities. And in annuities, we have a sequence of multiple cash flows. And we will first study Annuity Immediate, in which the sequence of payments starts at the end of the first period. So if the periods are 0, 1, 2, 3, and so on, usually it's number of years, but it could be anything. So the first payment will start at the end of the first period. The first period, remember, goes from time 0 to time 1. And so in Annuity Immediate, the first payment happens at time 1. The second payment happens at time 2, and so on. And the nth payment happens at time n. The numbers that are written below the line are the times, and the numbers that are written above are the payments, as is the usual convention in the time diagram. And so this is a special kind of annuity where all the payments are one, and the present value of this annuity is denoted by this symbol, and it's calculated by bringing all these payments to time 0. So present value means the value at time 0. So when you bring this payment of 1 at time 0, you multiply it by the discount factor nu. And the second payment, so this is a nu. And the second payment, when you bring it back to time 0, you're bringing it through 2 periods. So it comes through nu square. And similarly, the third payment at time 0 becomes nu cube, and so on. The last one becomes nu to the n. And so the present value equals this expression. And now this is a geometric sum, which can be evaluated if we use the formula of geometric sum. We know that the formula for geometric sum is a times 1 minus r to the n over 1 minus r, where a is the first term, r is the common ratio between consecutive terms. And so in this case, the first term was nu. Yeah, the first term is nu. The common ratio is also nu, because if you divide any two consecutive terms, like nu squared divided by nu, you get nu. So for a is nu, r is nu. So you substitute that, and therefore the present value comes out to be this expression. And now we also know that nu is equal to 1 over 1 plus I. And if we substitute that, this nu becomes 1 over 1 plus I. Here we have 1 minus 1 over 1 plus I. And if you do the algebra and do the simplification, you end up with this equation. And this will be our most commonly used equation for the present value of an annuity immediate where the payments are 1. But most of the times the payments are not 1. So if the payments are each x, then we just multiply this expression by x. And so the present value becomes x times this an hat. And so when you substitute the value of an hat, the present value becomes this. And 25.4 is the one that we use most commonly. Now the accumulated value at time n. So this is the present value, and now this present value is at time 0. If instead you want the accumulated value at time n, then in general, you just send the present value forward n periods through this interest rate. And so you just multiply the present value by 1 plus I to the n, because remember, present value is sitting at time 0. If you want to send it to time n, there are n periods. And so you multiply it by 1 plus I to the n. All these formulas, remember, are for the compound interest, because this one can be used no matter what it is, but okay, even here it has to be compound interest because this mu is the discount factor that is related to compound interest. But the idea that we mentioned here basically can be used for any kind of interest, as we will see in one of the problems. So let's see. Okay, so we are here at the accumulated value. So we just multiply the present value with 1 plus I to the n. That takes you to the accumulated value. But if you want a similar formula to 25.4, then once you multiply this expression with 1 plus I to the n, this term becomes the 1 times 1 plus I to the n becomes 1 plus I to the n. And here the 1 plus I to the negative n and 1 plus I to the n cancel out, and you just get a 1, and the bottom is still I, and you have the x. So you have 25.6. So let's look at this example. After making the down payment and other initial costs, you take a loan of 85,000 from a bank at the start of a month to finance the house. You decide to pay the loan by making regular monthly payments at the end of each month for the next 10 years. If the nominal interest rate compounded monthly is 6%, how much will you be paying each month? So a very practical problem. You want to figure out your monthly payments on the house. So since the payments are happening monthly, so the n, which is the number of periods we will use in the equation 25.4, will be the months. So in this case, n is the number of months, and since there are 10 years, so 10 times 12 equals 120. So n equals 120 months. And we're given the nominal rate, I superscript 12 equals 0.06, and we would need the monthly effective rate. So this rate I should correspond to this period n. So if the period is months, if n is the number of months, then I should be the monthly effective rate. If n is years, then I should be the annual effective rate. So in this case, since n is in months, so the interest that we will use here will be the monthly effective rate. And if the monthly nominal rate is 0.06, then the monthly effective rate is I12 by 12, and that would be 0.06 by 12, that's 0.005. I'm calling it J, and that will be a very common convention for an effective rate other than the annual effective rate. We know that we generally use I for the annual effective rate, although that's no law that we should use that, but that's our common convention. And so anytime it's another kind of effective rate, like in this case, it's monthly effective rates, we'll be calling it J. So in this case, J is 0.005. So we rewrite 25.4 with J instead of I, and keeping in mind that n is the number of months. So we get present value is equal to x, 1 minus 1 plus I to the j, 1 minus 1 plus j to the negative n divided by j. And the present value is 85,000 because that's the loan you took today. And we have to find x. X is the monthly payment, and j is 0.05. So once you do the algebra on this, x comes out to be 943.67. So that's what you will pay each month for the next 10 years in order to pay off the loan.